Many people think that groundwater is an endlessly renewable resource because it usually is continually replenished by the rainfall and the melting snow. In some regions, however, it must be treated as a non-renewable resource because the amount of water that is available for recharge of the aquifer is significantly less than the amount that is being withdrawn. So we could save some of the water by, for example, showering a little bit less. An average shower uses about 2.5 gallons per minute. So if we shower for 5 minutes instead of 10 minutes, we're saving 12.5 gallons of water. So we can also save water by only doing laundry when a full load is met, or by not flushing the toilets as many times, as I said in the beginning. Remember, let it mellow. Okay. Also, we can use less water by not wasting water while we're washing the dishes and only using the necessary amount for these to be cleaned properly. So overall, just beware of the consumption of water that you're having as you are going about your daily life. For example, one of the places where the aquifer is being depleted quite highly is in the High Plains aquifer. So in theory, the aquifer occupies this large extent, this large area that is shown in the image. So it goes from South Dakota up in the north all the way down to western Texas. And the depletion in the groundwater that this aquifer has seen has been pretty severe in certain areas where irrigation has been practiced during extended periods of time. So these areas are primarily agricultural, as you know, and rely heavily on the groundwater for irrigating their crops because not much surface water is available to them. In fact, it is regions like this one that account for 30% of all the groundwater used for irrigation in the U.S. So again, this High Plains aquifer takes up a lot of the irrigation uses of groundwater, and as we saw at the beginning of lecture, irrigation itself is the major user of groundwater overall, at least in the US. And so the consequences of this area being so irrigated by the groundwater are starting to be noticed, as you're seeing in the image. These areas, especially in the southern part of the aquifer, are declining by even 150 feet in terms of how much lower the water table level is. So that's quite worrisome. As we will see later in lecture, sometimes ground subsidence can occur as a result from natural processes that are related to groundwater. However, the ground may also sink when water is pumped from wells faster than the natural recharge processes can replace that water that is pumped. So this is especially common in areas that are underlain by unconsolidated sediments. What happens is that as the water that was initially occupying the pore spaces in between the grains is withdrawn, the water pressure lowers, and so the weight of the overburden of those sediments is going to be transferred through the sediments instead of to the water that used to lay there. So now the greater pressure on the sediments is going to start packing those sediments closer and closer together, making them tighter to each other. As a consequence of this, the ground will subside. So basically, the pores where the water used to be are now empty pores. So because of the overlying pressure, those pores are now going to be filled by the overlying sediment, and so overall the ground will subside and sink. So one of the worst things about this subsidence is that there is no way to reverse the process. The pore spaces cannot be just made. They can't just be reopened. So once they have been filled by other sediment, they can't just be packed or opened back up. Many areas have seen ground subsidence. Areas in California and the San Joaquin Valley in Central California are very good examples of this. So the image that you have on the top left shows the valley's location. So this is the San Joaquin Valley in California. And you're seeing that the subsidence since about 1925 until 1970s or so was of about 30 feet. So somewhere between 8 and 9 meters in certain locations. So in this kind of black areas is where you have the most subsidence. Some areas of the valley only saw about 0.5 meters, but some areas did see all of the full 30 feet subsidence of the ground, which is just amazing. Subsidence also causes problems in the overlying infrastructure, like the picture that you have here on the top right, where clearly the soil right here has subsided more than the soil over here. And so you have the building basically shifting, which can cause problems later down the road, obviously. Overall, as you're seeing, California has been experiencing a serious drought condition in the last decade or so. From this graph, almost every year it has seen record high droughts, which is concerning, obviously. And it has had to pass different laws for water usage due to the availability of this precious resource, both in terms of water that has precipitated and as well as water usage from the groundwater supply. However, there are other areas aside from California that are also subject to subsidence. Areas in Arizona have seen this occur. In Las Vegas, Nevada, have seen this occur. New Orleans and Baton Rouge in Louisiana, and then areas in Houston and Galveston in Texas have all seen subsidence due to this groundwater pumping out, basically. So these latter two areas in Louisiana and in Texas, which are coastal areas, one of the added concerns about the subsidence of the soil in these areas is that there can be easier flooding, for example, especially in this Gulf areas, which are also propense to hurricanes. So whenever there is a water surge from the hurricane, obviously the effects are greater if the ground itself is being sinking. Outside of the U.S., areas like Mexico City have seen great subsidence. So as we saw in the earthquakes lecture, Mexico City is built on lake bed sediments. So they are unconsolidated sediments, and as subsidence has taken place due to the pumping of groundwater over the first half of the 20th century, some areas of the city sank about 6 to 7 meters, which is between 20 to 25 feet or so. So not just California is bound to sink. Don't worry, I'm not picking on them, but other areas have as well. Another environmental problem is the encroachment of salt water where groundwater used to be. So this usually happens in coastal areas. In this case, the groundwater resource is being kind of threatened by the salt water that is infilling areas where the groundwater, which was fresh, used to be. So the image on the slide shows this relationship actually pretty well. But what happens is that the fresh water is less dense than the salt water, and so it will basically float on top of the salt water. If there is a heavy withdrawal of that fresh groundwater, so most of this is taken up by the well, then the salt water is going to flow upwards and occupy the pore spaces where the fresh water used to be. So by doing this, a point will come where the withdrawal of the groundwater is sufficient enough so that the well is no longer pumping the fresh water, but now it's going to start pumping the salt water that is now occupying those spaces. And so obviously that is going to contaminate the fresh water that had been pumped before, as well as not allowing for any further pumping of the fresh water that is in fact remaining. So this we call saltwater intrusion or saltwater contamination. So this case is exacerbated in coastal urbanized areas. In these areas which are urbanized, there are no natural recharges as much as they used to be before. So urbanized areas tend to be made up of materials that are impermeable. So concrete is pretty impermeable. So whenever there is recharge or should be recharged by precipitation, that recharge isn't making it to the ground, to the areas underground, and so the groundwater is not being supplied with further amounts. A solution to this is to have recharge wells. So recharge wells are going to allow wastewater to be pumped back into the groundwater system. Another method that has been found is to build this kind of large recharge basins, as you're seeing in the image over here. So both of these methods have actually been implemented in Long Island and in New York. This problem was recognized in New York over 60 years ago, and so these methods have both been implemented, and they have seen that they have both helped in terms of avoiding the amount of sea water contamination or intrusion inside or within the fresh groundwater reservoir. Lastly, the pollution of groundwater is another very serious matter, particularly in areas where aquifers provide a large portion of the water supply. A common source of groundwater pollution is sewage, which includes an ever-increasing number of septic tanks, as well as an inadequate or broken sewer system or farm wastes, for example. So the sewage water that is contaminated with bacteria will enter the groundwater, and it can actually get purified within the aquifer. So through different chemical reactions that occur in between the sediment grains, through which the water percolates, it can actually get cleaned up. It can get purified. For this process to occur, though, a lot of time will be needed. The water will need to flow slowly in between the grains in order for those chemicals reactions to clean out the waste. So aquifers made up from unconsolidated sediments or detrital sedimentary rocks will tend to be good aquifers for the purification, as the water that flows through is flowing through the voids in between the grains and will do so slowly enough that they will be purified. However, in aquifers that are mostly made out of crystalline rock, like metamorphic rock aquifers, igneous rock-made aquifers that are intrusive, or some crystalline sedimentary rock aquifers, in those cases, the water will flow too fast in between the fractures and not be able to get cleaned out by any percolation that may occur. Other sources and types of contamination that also threaten the groundwater supply are things like highway salt, fertilizers, pesticides, industrial materials from the landfills, from holding tanks, from natural gas extraction, and things like mine tailings will also greatly contaminate the groundwater supply. So these sources can easily get into the groundwater supply and hence contaminate it. A common solution is that the source for contamination, once it's found, it will be eliminated. And then typically the groundwater supply is fully abandoned in order for the pollutants to just be flushed away and purified slowly. So this solution is typically the least costly and the easiest to do, but it means that the aquifer cannot be used for many years. To accelerate the process, sometimes the contaminated water is actually pumped up and it is treated. And depending on the size of the aquifer and the case that they're treating, the treated water is either injected back or there is natural recharge that is allowed to happen in order to recharge that aquifer. So this method is a lot more expensive and it is time consuming. And it can also be pretty risky because there is no way to really know with certainty that all of the contaminated groundwater was actually treated.